One visualization that can be useful during energy considerations is the energy bar chart, which is, like it sounds, a bar chart telling you the energy during some interaction. We'll do a couple examples here. I think that'll make it clearer than trying to exposit it in some theoretical fashion. So let's look here. The velocity of a tugboat increases from 2 meters per second to 4 meters per second in the same direction as a force is applied to the tugboat during 20 seconds. So the force is applied to the right, and the speed goes from 2 to 4. Fill in the missing bars for the work and kinetic energy bar chart for this process. So they've told us that the kinetic energy, the first circumstance here is 2 bars, whatever that is. And we know that since the kinetic energy is 1/2 mv square, if I double v, if v goes to 2v, then v squared goes to 4v squared, I pick up a factor of 4. So if the first one was 2 bars, then the ending kinetic energy must be not 2, but 8 bars. That's our first thing. Our second thing is to remember that the work is the change in the energy. There's only kinetic energy here, so it's a change in kinetic energy. So if we end with 8 and we started with 2, then there has to have been 6, because these things have to go that way. So here we say 2, 4, 6, and we end up like this. So this is our energy bar chart for the circumstance they give us there. All right? It doesn't really capture anything particularly new. It's just a different way of visualizing what's going on. All right, the velocity of a tugboat changes from 2 meters per second to 4 meters per second in the other direction as a force is applied to the tugboat for 20 seconds. Now we have to be real careful about how they drew stuff here. This little arrow is not the force being applied. It's just that time moves this way. The force, of course, has to be applied the other way because this thing has to slow down and then turn around. So they tell us that, again, let's represent the initial kinetic energy as 2 bars, and we still have that, that the kinetic energy is 1/2 mv squared. So it's still true that v going to 2v implies that v squared goes to 4v squared. We still have 4 times as much, and so we still end up with 8. 2, 4, 6, 8. And then it is still true that the work is the change in the total energy, and if we ended at 8 and we started at 2, we must have had 6 in between. So again, 2, 4, 6, which is to say the picture is exactly the same. That in terms of the energy bar chart, these are the same problem. You might think that's really weird because after all, the tugboat has turned around. It's going the other way, but energy depends on the square. Kinetic energy is the square of the velocity. It doesn't care about direction, just how fast you're going. What's ended up happening here is that something must have done minus 2 joules. In fact, let's duplicate and talk about that in a sec. We can think of this as saying that there's a force applying against the motion, and that at first that force must do minus 2 joules of work so as to stop the boat. But then it continues to go and it moves the boat from 0 to 4, and that would take 8, because in the end it has, after all, 8 units of work at the end, so that the force does 2 things of work, so that our final answer is that we have the 8 joules at the end that we would need. All right. And then you can see that the total of these two together is 6. So it does actually work out. It's just a little weird. A 20 kilogram box moving at 1 meter per second encounters a force of 15 newtons that pushes it in the same direction that it is moving. Construct a valid energy bar chart for this situation. Here we say, well, the initial kinetic energy is 1/2 times the mass times the speed squared, which is 10 joules. And the work done by this external force, since it's pushing in the same direction, is the distance times the force. So it does 60. And we know that since the work is the change in the energy, then it must be that the final kinetic energy is the initial kinetic energy plus the work. So our 10 plus 60 gives us a total of 70. And then, because everybody's a multiple of 10, it was easy to just say let 1 bar be 10, and we get the picture as it looks. Person massing 75 kilograms, gliding at 3.1 meters per second across a frictionless ice lake, suffers a headwind of 14 newtons that acts while the skater slides 20 meters. A headwind blows opposite to the direction of motion. So, person is moving this way and suffers a wind which is pushing against it like this, so as to slow them down. Construct a valid energy bar chart for this situation. Here we can compute that the initial kinetic energy is 1/2 times 75 times 3.1 squared, which when you do all of it works out to be just about 360, just a little bit more, but tenths of a joule and therefore kind of negligible on the scale. And that the external force does a work which is 14 newtons times 20 meters times -1 because it's opposite to the direction. Remember, it's always, in general, it's if this is the direction the thing moves and this is the direction the object suffers the force, we want this angle, which is clearly 180 degrees, and cosine of 180 degrees is that minus sign. So this thing starts with 360, but then loses 280, and therefore must end up with 80. And our scale here works out that they're all multiples, if you look, of 40. So we just say one bar is 40, and we get the picture that's drawn here. A 1 kilogram box is gliding westward at 10 meters per second on frictionless ice. A 12.5 Newton eastward force acts on it, so opposite to its direction. Alice produces the given energy bar chart, but Charlene argues that it cannot be valid. Who's right and why? Well, Alice has correctly marked the proper scale here. These things look like they're scaled correctly. We have this kind of thing, but it turns out Charlene has to be correct and Alice has made a mistake because of this. The kinetic energy cannot be negative. That's not because of it being an energy, it's because of the form of it. The kinetic energy is 1/2 mv squared, and all of those are positive, so the kinetic energy has to be positive. So while Alice might have drawn what would have been the correct work for a force over the distance that she used, whatever that turned out to be, her final result is no good. As soon as this thing has reached that amount, so here, this amount, the object will have stopped and then would turn around the other way. And so therefore the kinetic energy would have to go like this, because then the rest of the work, this part of the work, really should be in the positive region. Right? In the end, the key thing is that you can't do so much negative work as to make a negative kinetic energy. The system won't let you do that.